2.5 Correlation and Best Fitting Lines. Your essential questions: how can you use a scatter plot to determine the correlation of data? And how do you approximate the best fitting line for a set of data? Maybe you've seen a scatter plot before. So a scatter plot is a graph, and it's usually a bunch of points of data scattered all throughout the coordinate plane. So it's used to determine whether there is a relationship between the paired data. And there's different types of correlation. And right now we're just going to talk about linear correlation. So you can see that there are 3 coordinate planes here. The one on the left is a positive correlation, which basically means as x is increasing, so is y. So as my inputs increase in value, so do my outputs. The one in the middle, that's negative correlation. And we can see that as my x values increase, or as my inputs increase, my outputs are decreasing. And then the last one, the one on the right, there's really no correlation. There's just a bunch of points plotted in this coordinate plane, and we can't really see any kind of pattern. Now, if I bring a ruler out, maybe what I see on the left is some kind of positive sloping line, something that maybe would look like that. And that might be my line of best fit. In the middle, for the negative correlation, what I see is some type of negative sloping line, and maybe I would draw a line of best fit, maybe something like that. These are not exact. However, there is no correlation on the last graph, so there's no way that I can draw a line that could represent or estimate a representation of that data. So determining correlation. We're going to describe the correlation by each scatter plot. And it's really helpful to be able to describe a graph by looking at the labels on the x and the y axes, or on the input-output axes, or on the independent and dependent variable axes. So I noticed this graph on the left, the horizontal axis, the x-axis, the independent variable axis, well, that represents GPA. So I've got GPAs of 0 to 4. And the vertical axis, or the dependent variable axis, or what we like to usually think of as the y-axis, that's got absences. So think to yourself, what kind of correlation, describe what's happening here. So I notice as GPA increases, because we always go along that horizontal axis first, what's happening with absences? Well, hopefully you're noticing that as GPA increases, absences are lower for those students with higher GPAs. So that's how you would describe it. And we recognize, if we compare it to our different types of correlation, it's a negative correlation, because as GPA is increasing, absences are decreasing. As GPA increases, absences decrease. Which makes sense, right? The more you're in school, probably the higher your GPA, the more you're learning. All right, let's look at the one on the right-hand side. So on the right-hand side, my horizontal axis is about GPA again, but this time, my vertical axis is about motivation. So what's the relationship here? Well, I notice that as GPA increases, so does motivation. So this is going to be an example of positive correlation. As GPA increases, motivation increases. And then you can ask yourself a series of questions. Well, is the GPA high because the motivation's high, or is the motivation high because the GPA is high? Well, that would involve a lot more research that you would have to look into the different scenarios. But this is an overall view of what's happening. All right, so we're going to approximate a best fitting line, and we're going to do this graphically. And I just kind of did that on these examples up here, where I drew those best fitting lines to the best of my ability. They're not perfect, but they're pretty good, and then I could get equations for them. So when you have these scatter plots, you draw a best fitting line, and then you're able to actually come up with an equation for those best fitting lines, and then you can make predictions for future trends. Step 1 is to carefully draw a scatter plot of the data. So that's what we're going to do first. So in example 2, we have researchers have found that as you increase your walking speed in meters per second, you also increase the length of your step in meters. The table gives the average walking speeds and step lengths for several people. And we're going to approximate the best fitting line for the data. So the first thing we're going to do, step 1, is to draw a scatter plot of this data. We have a couple of rows of data. So the first row is the speed and the second row is the step. We'll make the speed our input, so that'll be our x-axis. And we'll make the length of your step the output, or the y-axis. So notice that I have a couple different rows here of that data. So to make a good graph, I need to think about what I'm going to label each axis and what kind of units I'm going to put. So again, I know that the speed is in meters per second, and I know that the length of your step is in meters. So I will let my x-axis be the speed in meters per second. And then I will let my y-axis be the length of the step. So how about step length? And that'll be in meters. Now I have to think about how I'm going to label my axes as far as the units go. So I notice that my shortest speed is 0.8 and my longest speed is 3.4. So I need to go from 0 to 3.4. And I think if I divided my x-axis up into quarters, I could do that pretty easily. So 1, 2, 3. So I'll make this 1 meter per second, 2 meters per second, 3 meters per second. So I'll be able to get to 3.5. Now along my y-axis, my step length, well, my shortest step length is 0.5 meters and my longest step length is 1.2. So I think if I went by tenths, that would probably be the best, but I'm not going to label every single one. So I'll go up to a half. So 5 tenths. And then 1 meter. And then that would take me up to 1.5, which is too much, but that's okay. All right, so now all I do is I plot the points that this table tells me exist. So at 0.8, which is going to be a little bit more than 0.75 or 3/4, I'm at a step of 0.5 meter. At 0.85, which is going to be a little bit further along on the x-axis, I'm at a step of 0.6. At 0.9, which is getting a little bit close to 1, I'm also at 0.6. 1.3 takes me to 0.7, so let's see, that's going to be a little bit past 1 1/4. 1.4 also gives me 0.7, so that's close to 1.5 meters per second. 1.6 is just a little bit past 1.5, and that takes me up to 0.8 meters. 1.75 also has an output of 0.8. 1.9 is really close to 2 meters per second. And that takes me to 0.9 meters. 2.15, so that's a little bit past 2 meters per second, is going to take me to a step length of 0.9 meters. 2.5 meters per second has an output of 1 meter. 2.8 meters per second. Okay, that's a little bit past 2 3/4. It's going to take me up past 1 meter, but not quite to 1.1 meter. So maybe here. Let's see. 3 meters per second has an output of 1.15. So maybe here. 3.1 meters per second has an output of 1 1/4 or 1.25. So let's see, 3.1 is not quite to 3 1/4. And then 1.25 is halfway. So maybe there. 3.3 now is going to be past 3 1/4. And we're going to have an output of 1.15. Oh, so it's dropping back down. 3.35 would not quite be to 3 1/2. We're going to have an output of 1.2. 1.1, I think this is 1.2. And 3.4, again, not quite to 3.5, so, but we're getting close and I'm kind of out of room. So how about there? I've plotted my data. So step 2, sketch the line that appears to follow most closely to the pattern given by the points. And then here's kind of the key, and this is what you're going to shoot for. There should be as many points above the line as below it. And get out a ruler. You're going to use a ruler, you're going to use a straight edge. So what you do is you take your ruler, you put it on your data points, you try and get it so that you have about as many points above as you do below, and you do it to the best of your ability. And if you can get a couple of those points on there, that's pretty cool too. So I think this looks pretty good. I think I'll go with that. Okay, next step. You're going to choose 2 points on the line. Estimate the coordinates of each point. They don't have to be any of the original points, but they can be. Or you can just estimate what they are. So we're going to estimate those 2 points. So let's see here. I'm going to say I like the 3. So I'm actually going to use one of the original data points. I'm looking at this one here, 3, 1.15. So I think I'll use that one because that actually fell right on my line. And then I kind of like maybe this point right here. That was 1/2, 1/2. Okay, so I got 2 data points. One of them was original and one of them wasn't. Now I'm going to find an equation of the line that passes through the 2 points from step 3. So any 2 points on this line you can use. If you found other ones, use other ones. I'll start by finding my slope. I'll take the change in y over the change in x. So I'll get 0.65. So I'll get 0.65 divided by 2.5. So I'm getting a slope of about 0.26. And then I'll use that slope in one of my points to get an approximation or to get an equation of this best fitting line. So how about I use point slope form? Y minus y1. How about I use that second point? 1/2, 1/2. Equals my slope times x minus another half. Okay, so if I add that 0.5 to both sides, and at the same time now I'll go ahead and distribute. So let's see, 0.26 times 0.5 is 0.13, and it'll be negative. And then I still need to add that half. So I think that positive 0.37. Okay. And does that look about right? My y-intercept there does look to be about close, somewhere between 0.3 and 0.4. So there's the equation of my best fitting line. Now I could use this equation to approximate the step length at any speed. And how about I make this in function notation? So how about instead of having y equals x, how about I do something like length as a function of speed? So how about, just for fun, we write this in function notation. So I'll do length as a function of speed is going to equal 0.26, and instead of x, I'm going to call this speed, or s, plus 0.37. So this will be my s-axis, and this will be my l-axis. So then I'm going to use that function, and I'm now going to use it to figure out when somebody is walking 4 meters per second. So then I want the L evaluated when my speed is 4. So that's going to be 0.26 times 4 plus 0.37. This will be 1.04 plus 0.37, or 1.41. And let's go ahead and give that unit, the units for that, and that's going to be step length, which is in meters. Again, an approximation, but using the data that we've collected, we can use this to model the length of anybody's step based on their speed. And these are used quite a bit. There's a creek just outside of Piercy. And I have a friend that's a hydrologist and is working in Stanley Creek. And he has collected a lot of data. This is data that has been collecting dates and rainfall and levels of water in the creek. And there's a whole lot of data here. So what happens is when you collect all this data over time, you're able to then make a scatter plot, and you're able to then realize that, hey, there's some kind of relationship between that data. And what he did was he then created this. Now, this is not a linear relationship, right? And it's changing over time. So, you know, one day of the week, the water's really at a high point because maybe there was a lot of rainfall. And then at other times during the week, there was not a lot of rainfall. The water level's pretty low and not flowing very fast. But that's one example where you can use data. It's just one example. There's so many places out there in the world where everybody's just collecting data constantly, and they're coming up with these models. And in order for them to create these functions that represent and can predict occurrences into the future, they have to use data that they've collected, and they have to use this process of what we call regression. And right now we're just doing linear regression, but you can do it for any type of function out there. And we're going to learn about all those different functions this year. So now let's use our calculators to create stat plots and then to do the linear regression for us. So the table here gives the price in cents of a first-class stamp over time. T is the number of years since 1970. We're going to use the linear regression feature of a graphing calculator to find an equation of the best fitting line for the data. So the first thing we're going to need to do in step 1 is we'll go to Stat, Edit, and we're going to enter 2 lists. So our inputs will be our first list, and our outputs will be our second list. So get your graphing calculator, and in your graphing calculator, you're going to hit the stat button. Now that is like the third row down, and it's in the middle, so it's the middle column. You hit stat, and then you hit edit. And then if you've got anything in those lists, you can just hit delete for every single one that you have something in. Now, my list 1 is going to be my X values or my inputs or my time, where here it's going to be years. So I've got, let's see, 1 and 4 and 5 and 8, 11. Oh, I notice 11 happens twice. So let's see, that would be 11 years after 1970. So in 1981, there must have been 2 stamp price changes. 15, 18, 21. You should use your down arrows to get up and down. Mine's an app on my iPad, so I'm doing it a little bit differently, but it's still the same idea. Then I'm going to go over to list 2, and I'm going to enter in the price of the stamps. So 8, and then 10, make sure that your data lines up. So it looks like I have 11 things in each column. So they match up. So part 2 now, we're going to find an equation of the best fitting line by using the stat calc feature. So let's see if we can match their equation. They got an equation of P equals 0.947T plus 7.71. We're going to use the stat calc feature to do that. So you're going to hit stat again, that same button, but this time you want to go over to the right to where it says calc, and you're going to want to hit the linear regression. Now notice below that there's a quadratic regression and a cubic regression. We'll get to all that, but right now let's do a linear regression. Press enter. 11 and 10 need to be equal. So I have an error. I just said that I should make sure that they are equal to each other. And I don't think I pressed enter after I did my last one. So 33. Let me press enter so I get down below. Okay, that can happen. So now I'll go back to stat, calc, linear regression. Let's see if it'll give it to me. There it is. All right, so did I get the same slope? I did. I got 0.947. So it's changing by about 9/10 of a cent per year. My y-intercept here is 7.71. So at time being 0, which was 1970, the stamp price was probably about 7 cents or close to 8 cents. All right, so it matches. Now, what are we going to do with this information? So to see that the data have a positive correlation, we're going to graph the data pairs. And to do this, make a scatter plot, and we're going to use the stat plot feature. All right. So what you're going to want to do is look in that first column. You're going to use 2 buttons here. You guys see where it says plot, and I think yours will say stat plot. I'm just using an app, so it looks a little bit different. You're going to hit the second button and the plot button, or the second y equals. Okay, so make sure that plot 1 is selected. You can choose the different type of plots you want, but I'm going to keep it on the first type of plot because that looks like a scatter plot to me. And then I'm going to hit graph. So I'm going to make sure that plot 1 is selected. Oh, there we go. Had to be on. It's an app for me, so it's a little bit more complicated than my actual graphing calculator. For you, just make sure that you hit plot 1 and that it's on, and I'm going to hit graph. And voila, there's my data, my scatter plot, all my data as points. Now what we're going to do, part 4 here, we're going to graph the regression equation in an appropriate viewing window. and the graph shows that the line fits the data well. All right, so here's how we're going to do that. In y equals, for y1, I want you to actually type the slope times, and we won't use the variable t, we'll use the variable x. So we're going to type in 0.947. Now the x key is right under mode, so your second column, third row down, use that x, plus 7.71. Okay, you're going to hit graph again, which is that last column at the very top row. And there's your line of best fit. So you can also do this using your graphing calculator, and I'll expect you to be able to do it both ways.